Right, we're going to look at periodicity. Very simply, periodicity means repeating pattern. And the periodic table is called that because there is a repeating pattern of properties of the elements. What you need to know is the pattern of properties across period 3 and down group 2. So, it all stems from an increase in atomic number, okay, and therefore an increase in the number of electrons. We know that the periodic table is in rows and periods, and we're going to be covering the following things: atomic radius, ionic radius, ionization energy, electron affinity, electronegativity, conductivity of electricity, and finally melting and boiling points. And we're going to see that there are patterns, and we're going to try and explain what those patterns are. So, the first two periods are quite atypical of the rest of the block. That's because the first period contains only hydrogen and helium. In the second period, the atoms are significantly smaller than the atoms below them, and as a result they have unusual properties. So the fact that nitrogen, oxygen and fluorine hydrogen bond, okay, is atypical of those groups. What we're saying is, at the top of the group, okay, there are different properties based on the fact that they are so small. So let's consider electron configuration. You should know this. As you go across the period, so you have a greater number of protons, and you have, therefore, filling of electron shells. We start off by filling the 3 s shells, then move on to the 3 p shells, and those are the electron configurations. Sodium through to aluminium are metals. Silicon is a metalloid. It has metallic properties, it has non-metallic properties, and the rest are all simple molecules, molecular substances, non-metals. Come in and not go in front of the camera, that would be good.
Yeah, that's what I did.
Excellent. So, typical properties. As you'd expect, the metals are shiny, the non-metals aren't, and so on. Metals are malleable and ductile, non-metals are brittle. Thank you. Yes, yes, yes. The metals conduct electricity, no surprise there, and the non-metals don't. Finally, the metals have a high melting point, and the non-metals don't. Okay, moving swiftly on.
You should be ashamed of yourself.
However, okay, not every element satisfies the simple criteria of metal and non-metal. Okay? Carbon is a good example. Carbon's got your non-metal form, which is your diamond, but it's also got a metallic form, okay, which is graphite. And in just the same way, silicon has some properties of both. Okay? Right, let's look at atomic radius. Very simply, as you go along the period, the atomic radius decreases. Now that's counterintuitive. You will want to say, you increase the number of electrons, therefore it gets bigger. Wrong. You increase the number of protons. The electrons are in the same shell, okay? Therefore the electrons are pulled tighter to the nucleus. Does that make sense? Yeah. Yep. Yes, sir. It's counterintuitive, but there we go. After atomic radius, well, just before we move on, you can't actually measure the position of the electrons around the outer shell easily. So what we do is we'd look at, say, a molecule of Cl2, and it's quite easy to identify where the nuclei are. And if you know how far apart the nuclei are, you can say, well, half that distance got to be the radius of chlorine. Does that make sense? Yeah? If you've got 2 chlorine atoms, half the distance between them, that's got to be the radius of chlorine's electrons. So that's how they're measured. If we go to ionization energy, this is where it gets a bit trickier. Ionization energy is the energy required to remove an electron from a mole of gaseous atoms. It's got to be gaseous or gaseous, and it's got to be 1 mole. As you go across the period, the general trend is that it gets harder. And it gets harder because you have more protons. So, sodium, 11 protons, 3s electron, and so on. As you go across the period, the number of protons increases, but it's important to realise which electron you're removing. When you've got sodium, you're removing a 3s electron, magnesium, a 3s electron, aluminium, a 3p electron, and so on. And then the only other bit you've got to pay attention to is the difference between phosphorus and sulfur. Sulfur, you are removing a paired electron. Excellent. And you end up with a graph that looks a bit like this. And what it shows is that as you go from sodium to magnesium, the ionisation energy increases. It's harder to remove an electron because it's got greater nuclear charge. However, when you go from magnesium to aluminium, you're now removing a p electron, which is in a higher energy level and takes less energy to remove it. From aluminium to silicon to phosphorus, patterns restored, greater nuclear charge, harder to pull an electron off. From phosphorus to sulfur, in sulfur you are removing one of a pair, and that means it is being repelled by the other electron. Electrical conductivity. From sodium to magnesium it increases, from magnesium to aluminium it increases, and then it doesn't. Okay? Here you have a metallic structure, one delocalized electron. Here you have a metallic structure, two delocalized electrons. Here you have a metallic structure.
Why is there such a big increase from magnesium to aluminium and not so?
It's beyond the scope of the syllabus, okay? But there is a significant increase. You just need to know that it gets bigger. Sodium to magnesium to aluminium, big increase, okay? Because you have more delocalized electrons. However, silicon through the rest, okay, no delocalized electrons, doesn't conduct. Finally, a nice straightforward trend. As you go across the period, the electronegativity increases. Okay? More protons, greater pull. Except that argon isn't quoted. Why is argon not quoted? Noble gas, so
Can't form a bond.
can't form a covalent bond. Remember, electronegativity is the ability of an atom to attract electron density to itself from a covalent bond. Melting point. Okay? Shh. Sodium to magnesium to aluminium increases melting point because you get increasing number of delocalized electrons, greater attraction between the ions and the delocalized electrons. Can you pause, please? Right. From sodium to magnesium to aluminium, more delocalized electrons, higher charge on the nucleus. Okay? Therefore, greater attraction between the nucleus and the delocalized electrons, stronger bonds, higher melting point. As you go to silicon, you've then got a giant covalent structure and the melting point increases significantly. After that, you're dropping down to P4, okay, which gets significantly lower. You now only got to break van der Waals forces. After that, S8, so it's going to go up a bit because S8 is a bigger molecule than P4 and therefore has more electrons. After that, down to Cl2, smaller, okay, so less electrons. And finally, Ar, smaller still, less electrons, weaker van der Waals forces. Okay? You should know that it's a giant covalent structure, that it's P4, S8 and Cl2. Boiling points we're not going to worry about, and that is periodicity. Pause please.